Good afternoon. We're going to get started. We're going to keep working on chapter 27. Does anybody have questions before we get started? Anyone? All right. Okay, so where did we leave off last time? We're talking about reaction of monosaccharides as alcohols. And so what we did was we started off with a glycoside. You'll recognize this as a glycoside because instead of an OH at the anomeric carbon, we have an OR group, some sort of OR group that makes it a glycoside. So rather than the anomeric carbon being a hemiacetal, it's an acetal. So that's a glycoside. I hope you are able to recognize that. And what we did, we started with the glycoside, and what we did was we basically deprotonated every hydroxyl and treated it with methyl iodide excess. So every single free hydroxyl is methylated. And once we do that, these are now methyl ethers, and they're very stable. In order to cleave a methyl ether, you need to use hot concentrated hydroiodic acid, which is really strong conditions. So these guys stay, but this is still an acetal, and we know that acetals come off very easily in the presence of acid. So that's part of an acetal, sensitive to dilute acid. So on the next page, we can see that if we treat this with dilute acid, then all the methyls that are on the free hydroxyls are going to stay, except for this one. That's going to be converted into a hydroxyl now. All right, so I'm just going to draw a squiggly line here to show that I have alpha and beta. And the rest of these are ethers, and they're going to stay. And certainly this other one here, this OCH3 here is also going to stay. So before, when we had it as a glycoside, we did not have meter rotation. So for this compound on the previous page, since it's a glycoside, no meter rotation at all. But once we hydrolyze that acetal and make it a hemiacetal, now meter rotation can take place. So having all of those hydroxyls, having these methylated does not interfere with meter rotation. So what's going to happen, again, for meter rotation is that as soon as this becomes a hydroxyl, now the ring can open and close and open and close and open and close to give us an equilibrium mixture. Okay, so that's what's going to happen here. All right, we can also esterify. So these are just reactions of alcohols, the same things that we did back in chapter 9. We can esterify, so we can use acetic anhydride and pyridine. This is alpha D glucopyranose. And of course, we would need excess here. And what we're going to basically do is we're going to acylate every single free hydroxyl, including the one at the anomeric carbon. And so here's what the product would look like. And I'm just going to use AC for the acyl group. So AC equals an acyl group. All right, and if we wanted to name this, this would be alpha D glucopyranose pentaacetate. All right, so the names that we're using here, the nomenclature in this chapter is very descriptive and tells us exactly how to draw these compounds. So in biological systems, the most important esters of sugars are phosphate esters. I'm not going to be testing you on biosynthesis of glucose 6-phosphate, but it's just, this of course starts off the process of glycolysis. All right, so what we're doing here is we're making a phosphate ester here at this hydroxyl, right? So that's this. That's all it is. Similar concept. Notice that's only happening at the primary. It's only happening at the primary hydroxyl. All right, not going to be testing you on that. That's biochem, right? Unless you want me to. Okay. All right, should we finish labeling that though? This is just for fun. Come on, I'm not going to test you on this, but glucose 6-phosphate. And this is ADP, adenosine diphosphate. All right. Let's talk about oxidation reactions of sugars, and so some of these reagents are going to seem familiar to you, hopefully. There's one thing that's new is talking about reducing sugars versus non-reducing sugars. Reducing sugars are sugars that are easily oxidized by mild oxidizing agents. If you hit all sugars with a strong oxidizing agent, they'll be oxidized, but we're talking about mild oxidizing agents. So examples are glucose and fructose. Non-reducing sugars, of course, are not easily oxidized by mild oxidizing agents, and the reason that they're not easily oxidized is that the carbonyl group is tied up in an acetal linkage, so they're glycosides. All right, so here's some examples here, and I want you to be able to recognize whether a sugar is a reducing sugar or non-reducing sugar. And what you're going to look for is you're going to look for the anomeric carbon. If there's more than one sugar, you're going to look for the anomeric carbon on both sugars. If one of them is a hemiacetal, then that's a reducing sugar. If there are no hemiacetals and anomeric carbons, it's a non-reducing sugar. So let's see what we're talking about here. All right, so you look at this one here. This is methyl beta-D glucopyranoside. And what we want to do is we want to key in on the anomeric carbon, and this is the anomeric carbon here is a glycoside, or is an acetal if you want to think of it that way. And so therefore this is a non-reducing sugar. And that's because the anomeric carbon is tied up in an acetal linkage. So in order for this sugar to be oxidized, it needs to be in the open chain form. So it needs to be able to open up. If it can't open up, then it's a non-reducing sugar and it's not going to be easily oxidized. So it's oxidized from the open chain form. And so we know that glycosides do not undergo mutant rotation. That ring does not open, and therefore they're not easily oxidized. All right, here's another example here, and we want to find now we have a disaccharide. We want to find the anomeric carbon on both. So here's the anomeric carbon on this sugar. And here's the anomeric carbon on this sugar. And it's the carbon that's bonded to two oxygen groups here. So we have a lot of alcohols here all throughout. We want to zero in on this one here because that carbon here has an OR and an OR, and this carbon right here, OR and OR. So both anomeric carbons are tied up as acetals, so it is a non-reducing sugar. So this is sucrose, or table sugar. And it is a non-reducing sugar. And that's because the anomeric carbon is an acetal. Or you can also say glycoside. Glycoside is specific to sugars. Anomeric carbon is an acetal, so a glycoside. All right, so both of those are not going to react with mild reducing agents. But if you look here, we're going to talk about Tollen's reagent, and that's a mild oxidizing agent. And this is going to oxidize aldoses to aldonic acids. All right, so if you look at this sugar right here, this is a reducing sugar. So it gets a little confusing. It's a reducing sugar, that means it's easily oxidized by mild oxidizing agents. So that's a little confusing, but remember, when you add an oxidizing agent to the sugar, the oxidizing agent is itself reduced while the sugar is oxidized. So it is a reducing agent, but I can see how that would be a little confusing here. All right, so Tollen's reagent oxidizes aldoses to aldonic acids. So this is, since this anomeric carbon is a hemiacetal, that means it's a reducing sugar. And so this is alpha D glucopyranose. A hemiacetal. All right, so that means that the ring can open up, and once the ring opens up, this is now open chain glucose, and when it's open, then it's oxidized. And so the reagent is silver nitrate in aqueous ammonia. So that's Tollen's reagent. And basically, this is a very mild oxidizing agent. It's really only going to oxidize the aldehydes. Okay, it's not going to oxidize any of the other hydroxyls. And so that's why it's mild. And so what you're going to get is the aldehyde oxidized to a carboxylic acid. Everything else stays the same. Even the primary alcohol on the end is not oxidized. And this is called an aldonic acid. So that's the generic term for a sugar that's been oxidized just at the aldehyde. It's an aldonic acid. If we want to be more specific, it would be D-gluconic acid. So that would be a more specific name, D-gluconic acid. We also get a silver mirror, which is kind of cool. This is how you can make take a round bottom flask and turn it into a mirrored round bottom flask, which is kind of cool to do. So this is a silver mirror on the inside, deposits on the inside of the flask. All right, so that's some Tollen's reagent. And then bromine in water also oxidizes aldoses to aldonic acids. Yes?
Does it change both ends?
No, it doesn't. We're going to talk about a reagent that will. Nitric acid will, but not this reagent. Okay? So bromine water also oxidizes aldoses to aldonic acids. The product is an aldonic acid again. That would be the generic term. If you make an aldonic acid of glucose, it's gluconic acid. If you make an aldonic acid of mannose, it's mannonic acid. So you kind of get the idea. All right, so this here is the C2 epimer of glucose. You noticed that right away, right? This wasn't glucose. Okay, so if it was glucose, then this hydroxyl would be equatorial, and it's not. And remember, we number from the right-hand side here. So it's the C2 epimer of glucose, which happens to be mannose. You don't need to know that, but it is. Now, most of mannose is going to be in the ring form. Very little, very small amount, less than 1% open chain. But once it does open up, and it's going to go back and forth between alpha and beta. And I'm showing here the squiggly lines for a mixture of alpha and beta. So remember, we talked about that meter rotation. We're going to get a mixture of alpha and beta. We're going to get an equilibrium mixture. This equilibrium mixture will not exactly match glucose because it's a little bit different. It has one of the hydroxyls in the axial position, so there's going to be a different percentage, but we could calculate it like we did glucose if we had those optical rotations. All right, so this is open chain mannose, D-mannose. So bromine in water also is going to oxidize that to a carboxylic acid. Just the aldehyde. Notice I'm remembering to put hydrogens in. You've got to do that on the final. So generic, aldonic acid. Specific, mannonic acid. D-mannonic acid. Let's be as specific as we can. D-mannonic acid. Now, and what's going to happen with the D-mannonic acid is it's going to want to cyclize. And so I'm going to have a long arrow here. It's on your page. It's on this next page here, but it's going to want to cyclize. So here's what it's going to look like. Notice all the rest of the hydroxyls are untouched. And so basically what this is an ester in a six-membered ring. So this is a lactone. So this is mannonic acid, D-mannonic acid lactone. Everybody see the ester here? Let's circle the ester right here. So lactone is a cyclic ester. And lactone is favored in acid and disfavored in base. All right, so since this is bromine in water, and when you have bromine in water, you get some HBr in this solution. So it's acidic solution. And so the lactone is favored in that. The reason we didn't get a lactone on the previous one is because this is base. Okay, so let's go back. If you want to go back there and say that this is, lactone is not favored in base. Which is why I wrote the open chain form in the product here. So ammonia is a base, this bromine water is acidic solution, so we tend to get these things in a six-membered ring, lactone. Questions on that point, anybody? So we have two different reagents to make a lactone. One, the open chain is going to be favored, and then the second one, the ring closed. So what it looks like, is that we've really it looks like all we've done is oxidize this hydroxyl when it's in the closed position, but it's not. It does open up, it's oxidized, and then it closes back down again. And so that's what you get. All right, nitric acid is stronger. So if you've already gone to discussion this week, we've talked about nitric acid. It is a stronger oxidizing agent. It's going to oxidize the aldehyde, and it's going to oxidize the primary alcohol on the other end. So HNO3 in heat. So this is open chain. What sugar is this? Everybody recognize that sugar? If you don't, good idea to recognize that by next Wednesday. Open chain D-glucose, right? So that's open chain D-glucose. When we oxidize that, we get both ends oxidized to carboxylic acid. It is slower to react with secondary alcohols, so the secondary alcohols are not touched. So oxidizes aldehydes. And primary alcohols. This has a different name. It is an aldaric acid. So generic for all sugars, aldaric acid. And specific, since this is glucose, D-glucaric acid. All right, so do you have to memorize the term aldaric acid? No. If you know what nitric acid does to a sugar, then you don't need to know what aldaric acid is. Okay? As long as you recognize what the reagent does, then you will be in good shape for the final. Questions on nitric acid, anybody? A couple more reactions that we want to talk about, and then we're going to just move to talk about disaccharides. All right, so lengthening and shortening chains in carbohydrates. And how you do that, we're going to talk about lengthening the chain first using Killiani Fischer synthesis. And then we'll talk about shortening the chain. And then we'll look at an example of how you would use these types of reactions to figure out the structure of unknown sugars. And then we'll look at more reactions, we'll look at more problems like that at the final review that's on Friday. Okay? So I couldn't put it on the discussion worksheet because we hadn't covered it yet. All right, so this is Killiani Fischer synthesis, and the reagents should look a little bit familiar to you. HCN, we did it differently in chapter 21. So this is chapter 21. We did it step 1, NaCN. Step 2, H3O+. Well, what do we do with, what does that do? What do those reagents do with an aldehyde? Remember that from chapter 21? Make a cyanohydrin, right? All right, so basically what I have here is this part of the molecule is not changing. So rather than taking the time to draw all of those boxes, we're just putting ditto marks to say that's staying the same, and we want to just focus on what is actually changing in this molecule as it reacts. So we're going to make a cyanohydrin. So remember how that goes. We protonate oxygen first. If we do it with HCN, and then the cyanide attacks. If we do it in the two-step process, boom, like that, right? If we do the two-step, the cyanide group attacks the carbonyl without protonating first, and then you add acid. Okay, so that's two ways to do it. But when you do that, you're going to add a new stereocenter. Because that is a new stereocenter, and since these are achiral reagents, it means we will get 2 enantiomers for our product. All right, and again, the rest of the molecule is staying exactly the same. And then, I don't know how they did this back in the day. Emil Fischer, before we had a lot of the techniques that we have now. And he, I don't know how he worked with hydrogen cyanide without efficient fume hoods back then. I don't know. I don't know how he did it without dying, honestly. He did end up dying with one of the reactions we have coming up here. So anyway. So H2 palladium barium sulfate. So basically what this is going to do is it's going to partially reduce the nitrile. Because of the barium sulfate, it's a little bit reduced reactivity, so we're not going to go all the way, we're not going to reduce the cyano group all the way to a CH2NH2. We're going to stop at an imine. And so what it looks like after that step is so hopefully these reactions are looking familiar to you, although this is a little bit different. But what is that functional group at the top there? Again, back to chapter 21. What is that functional group at the top there? It's an imine, right? What happens when we put an imine in acid? What happens? What's more stable, an imine or the corresponding aldehyde? Aldehyde's more stable, so it's actually going to be converted into the aldehyde. So it's almost like we've inserted a CHOH into the sugar in the 2 position. So we've extended the chain by 1 carbon, and we have a pair of sugars, epimer. These are epimers of each other. And so if we draw the rest of the molecule, we'll see. Should we? Let's do it. Let's take out that. Let's draw the rest of it here. What's the bottom part? This is just D-glucose, right? Oops, let me move that over. And you'll recognize that as glucose, right? D-glucose. And when we draw the other one, again, the bottom's going to be exactly the same. Has not changed at all. This is the C2 epimer of glucose. Which we've already seen a couple of times. This is D-mannose. All right, question on Killiani-Fisher synthesis. Yes?
For the second step, after you add the H2 palladium, how come it doesn't completely reduce?
It's the barium modifies the reactivity of the palladium. Tones down the reactivity of the palladium, yeah. All right, so that's how we add a carbon. We want to talk about how to take a carbon off. And your book has wool degradation, and I'm choosing rough degradation instead. Yeah. You can draw the cyclized. I just drew it open chain. Yeah, it's certainly going to mainly be cyclized product. All right. So I'm using rough degradation because these reagents are a little bit more familiar to you. But it's a way to shorten the chain. So bromine and water. We already talked about what that's going to do. The calcium hydroxide is just there to remove any of the acid that's present. As we said, when you have bromine water, you do have some HBr. So that second step is just to deprotonate and neutralize any acid that is present. And then these reagents are not familiar to you, but it's H2O2. You'll recognize that as an oxidizing agent. And Fe2SO43. So oxidative decarboxylation. And what happens is this CO2 that's on the top right here goes away. And I drew this wrong. I have to put an OH here. I think I drew it and it just erased it for me. It does that sometimes. And then, so this goes away, and then the top, this carbon number 2 right here ends up becoming an aldehyde. All right, so let's draw that back again. So top carbon is converted to CO2, and then the second to the top carbon gets converted into an aldehyde. And you can do this stepwise. We talked about in the beginning when we talked about D and L sugars, you can take a carbon off at a time until you get to the bottom. And that's how Fisher was able to assign configuration for L sugars and D sugars. All right, so the rough degradation can be used in structure determination. Here's an example here. And we'll see some more examples on the final review and maybe on the final. What do you think? All right, so here's an example. And what I recommend that you do is you read through the Fisher proof of structure that's in chapter 27 so you can see how all these reactions are used to determine how Fisher was able to come up with the structure and assign all of the stereocenters in glucose without any of the modern technology that we have now. It's pretty amazing that he was able to do that. Okay, so here's an example. D-altrose is an aldohexose. So that means it's 6 carbons, and it's not a ketose, so it has an aldehyde at the top end, right? Rough degradation of D-altrose gives the same aldopentose as does degradation of D-allose, the C3 epimer of glucose. Give the structure of D-altrose. Okay, so I'm going to draw it over here. I know what D-allose looks like. I know what it looks like because I've been given the information. It's the C3 epimer of glucose. So if we number from the top, 1, 2, 3, 4, 5, 6. C3 epimer, so that means we have, this is the same as glucose, carbon number 4 is the same as glucose, carbon number 3 on glucose, the hydroxyl would be on the left, but now it's on the right. And on glucose, the hydroxyl is here. So that's D-allose. And when I had to memorize all the structures of the sugars when I was a student, that was really easy to memorize because all of the hydroxyls are on the same side. All those, see? Yeah. But it sticks with you. That's stuck, and that's the only one that that's one of the few I have memorized. Okay, so that's D-allose, which is the C3 epimer of glucose. So at a minimum, you need to memorize glucose, otherwise you're not going to be able to solve any of these types of problems. And what it says is that, that D-altrose is an aldohexose that gives the same aldopentose as does degradation of D-allose, the C3 epimer of glucose. So let's do a rough degradation of this one here and see what we get when we do a rough degradation. All right, so remember what happens here is that this is oxidized to a carboxylic acid, and then we do oxidative decarboxylation, so this comes off, and then carbon number 2 is converted into an aldehyde. So let's draw that. So carbon number 2 is now our aldehyde. Would everybody agree that that's the product you would get from rough degradation of D-allose? Everybody see that? All right, so if you're going from the bottom, everything's staying the same. That carbon's the same, that carbon's the same, that carbon's the same, that carbon's the same. The only thing that changes is the top 2 carbons. That's gone, and that becomes now carbon 1. All right, so what that means is that if they form the same sugar on rough degradation, that allows us to draw the structure of D-altrose. So what we're seeing here is that, let's number this. When we do a rough degradation, this part of the molecule stays exactly the same. So let's draw a square around that part of the molecule staying exactly the same. And so that means that this part of the molecule is staying exactly the same. So it means that this is D-altrose. Questions on how I did that? So there's only 2 possible configurations at the stereocenter. Here has the hydroxyl on the right, here has the hydroxyl on the left. And so if the hydroxyl was on the right, it would be D-allose. It's not. It's D-altrose, and so that means that that's the structure of D-altrose. Questions? Anybody? Too easy? Too easy for the final, you think? I heard a yeah out there. Okay. All right. The last reaction we want to talk about were sugars. You're familiar with this reaction. Sodium borohydride, what does it reduce? Aldehydes and ketones, right? Okay? It needs to be in the open chain form for this to work. Okay, so we're going to reduce this. Aldehyde's going to be reduced to a primary alcohol. And if you've gone to discussion already, some of you have, some of you haven't. Once you make both ends of the sugar the same, you can look for planes of symmetry here. And so here's another example of making both ends the same. We have 3 stereocenters right here. Okay, so when we oxidize, when we reduce the aldehyde, we still have 3 stereocenters here. But notice once we reduce, I keep wanting to say oxidize, once we reduce the aldehyde, both ends are the same, and we actually have a plane of symmetry right here. If we slice right through that hydrogen-oxygen bond and the hydrogen on the other side, this molecule is actually a chiral. And this is another thing that Fischer used in his proof of structure of glucose. Things like this to assign configuration of sugars. Questions on reduction of sugars? Anybody? Let's talk a little bit about disaccharides. We've already mentioned that if you take the anomeric carbon of a sugar plus an alcohol, you have an acetal, which is a glycoside, right? If if the alcohol is another sugar, you have a disaccharide, which is composed of 2 monosaccharide units. In naturally occurring disaccharides, there are 3 principal glycosidic bonding arrangements. I'm going to give you an example of each of these. So, and I want you to be able to identify these. If I give you the structure of a disaccharide, I want you to be able to indicate what type of linkage you have. All right? It's not that hard. A 1,4' link, the anomeric carbon C1 is bonded to the oxygen atom on C4 of the second sugar to form a disaccharide. The prime symbol in 1,4' indicates that C4 is on the second sugar. I'll show you what that means in just a second. A 1,6' link, the anomeric carbon C1 is bonded to the oxygen atom on C6 of the second sugar. And at 1,1', the anomeric carbon of the first sugar is bonded through an oxygen atom to the anomeric carbon of the second sugar. Okay, so let's look at some examples of each of these. So this is lactose. All right, so one of those monosaccharides that makes up lactose is glucose. Which one is glucose? This one or this one? That's glucose. Which epimer of glucose is this one? 1, 2, 3, 4. C4 epimer of glucose. Okay? So we want to look at we have 2 anomeric carbons here. Anomeric carbon is an acetal here. So it's a glycoside. We have a second anomeric carbon because we have a second sugar. Here's our second anomeric carbon. Is a hemiacetal. All right, so, and this first sugar right here is galactose. You don't need to have that memorized. I would tell you what that was. Our first sugar is degalactose. And the first sugar is usually drawn over to the left. In fact, that's the way I'm going to draw it for you. So this is galactose. The C4 epimer of glucose. So first sugar drawn over to the right, second sugar over here is glucose. And notice here that this is this carbon right here, the glycosidic carbon there, is that alpha or beta? It's beta, right? So this is beta. And so sugar number 1 is bonded to sugar number 2 through the oxygen on carbon number 4. 1, 2, 3, 4, right? It's bonded through the oxygen on carbon number 4. So this is a beta 1, 4'. Sugar number 1 is galactose, so it's a galactosidic linkage. Beta 1,4 prime galactosidic linkage. And the galactosidic linkage, that's because sugar number 1 is galactose. All right? Questions on how I did that? So beta 1,4 prime galactosidic linkage, maltose, which is a starch, is a 1,4 prime glucosidic linkage between 2 glucose units. So that means that the first sugar is glucose and the second sugar is glucose. All right, so we're looking for anomeric carbon here. Anomeric carbon is an acetal, so it's a glycoside. That's the thing we want to label. Here's anomeric carbon number 2. Is a hemiacetal. All right, so what is the orientation of the hydroxyl in carbon number 1? It's alpha, right? This is alpha. And we are bonded through 1, 2, 3, 4. We're bonded through the carbon number 4 of our second sugar. So this is an alpha 1,4 prime glucosidic linkage. Now, are either one of these reducing sugars? They're both reducing sugars. So we will not oxidize this ring at all, but this ring can open and close, and so can that one. So they're both reducing sugars. Well, we'll talk more about that next time.